So I think we have almost everybody. So so first I would like to thank the organizers for the kind invitation to the Newton, which is a really wonderful place. So I know it's Friday afternoon. This is the last talk of the week, and so I will try to make it simple. But so this, as I've written here, it's joint work with Scott Sheffield, and that is not published yet. So so it's about quantum gravity. So I'm going so I'm not going to describe all of quantum gravity, but I'm going to give you a hint how large deviations appear in quantum gravity and help you to actually prove some rigorous results in it. So so first, a snapshot of what is 2D quantum gravity. I mean, one approach to 2D quantum gravity, which is so first of all, if you do, so I will be in 2 dimensions, and I will deal with random lattices. But before that, if you do standard statistical mechanics on a regular lattice, this is what we have seen this morning with Tony Gutman, who unfortunately doesn't seem to be here. Have you seen him around? No. Okay. I should have told him there was a talk, but anyway. So this is the standard way of doing statistical mechanics using discrete lattices, regular lattices, and typically what you have in the models I have in mind in what I'm going to describe, even so you are not going to see much of those models, will be random lines on a regular lattice when you are on the discrete level. So random lines could be, for instance, suppose you are in percolation. These random lines would be just boundaries of occupied clusters. If you are working with the Ising model, for instance, that would be simply here. You would have Ising spins, and those red lines would be boundaries of domains, Ising domains. And of course, sometimes you look at correlation functions. And for instance, in the Ising case, then you have, for instance, often you have open paths which are wandering from one point to another point. So if you do quantum gravity at the discrete level, that corresponds to do it on a random lattice. So you first choose a model for random lattice. So one favored one, for instance, is a randomly triangulated lattice, which is made of the same triangles as before, except that before we had a constraint that you should have a certain number of triangles around one site, and now we do it random, so it means that of course the connectivity is a fluctuating variable, and typically you will have, instead of hexagons, you will have pentagons, heptagons, and higher and lower connectivities. So this is an example of a random planar triangular lattice. I'm not going to use that today at all, actually, but just want to give you a hint of the models with which the physicists started, something like more than 20 or maybe 30 years ago already. And if you do now, so remember we had this statistical mechanics model on a regular lattice, and now you have your random lattice, and now you put the same model on your random lattice, and typically that could be the same Ising boundaries or the same percolation boundaries, for instance. Or if you had self-loading walks, like we saw this morning, forget about the loops. There could be a self-loading. Take only one, that would be one of these self-loading polygons that Tony alluded this morning to. And if you take an open path, that would be one self-loading walk. But of course, if you have many loops, you are going to have another model, like an Ising model or a percolation model. And Potts models are the same. Okay, so typically, just to give you an idea of what the people look at, they do. So you take one random. So they take random planar graphs. So they are all planar. They can be either they can have the topology of the sphere, or they can have the topology of the disk. And then once you have your random planar graph, you put your chosen statistical model on M on the random planar graph G, and then what you do, you calculate the partition function of your model for a given graph, then weight your graph a la Gibbs, typically with the exponential of minus beta times the cardinal of the graph, which describes your discrete area, right? So it means and then you resum over the graphs. So it means you just resum the partition functions for any given graph, and then you resum them over all planar graphs, putting a certain weight, which is actually giving less and less weight to the bigger graphs.
Does the inverse temperature beta also enter into Z of G?
No, because Z of G depends on the parameters of the model you have put on the graph. But beta is not really the inverse. Beta is what is called the cosmological constant in field theory. So, because that's something which describes the size of your universe being this large graph. But thank you for the question. Beta looks like a temperature. It looks like Gibbs, but actually it's just a free parameter. And inside here, you have something else. For instance, you will have the temperature. You will have a one coupling constant for Ising model, the combination of J, the coupling constant, and the temperature. So there are two independent parameters. And this is why I have put here a double critical point, which I will come to in a minute. But this set Z of G sub G depends on at least one parameter for a given model, but sometimes many parameters. Yes?
So you say it's a random planar graph, so how
yes.
exactly is it chosen?
Well, I don't want to go into these details because there are precise ways to define them. Usually the calculations originally the calculations were made with random matrices because these are the graphs generated by the large n limit of random matrices models, like trace of m cube, a trace of m4, which generate 4-leg coordinated vertices. So this has been understood since a long time, and then they give you a certain way of doing statistics. But somehow you can also rebuild the statistics with weights and labeling and proper, proper symmetry factors, so that you can understand. But there is also another approach, which is the approach which you have seen in some of our other workshops. In particular, in the last workshop, when you had these people doing random maps, planar maps, but doing them, in the combinatorial way, by bijections to trees. So they are also, you can also generate them with trees, decorated trees, and then you generate your random planar maps, which are the same ones. But I'm not going to use that at all today. I just want to give you an idea. And of course, usually you want to have both your graph to be big. You want to take the continuum limit of your graph, and you want to take the continuum limit of your paths, of your random lines, so you will have a double critical point for G and for the planar graph and for the model M. And actually here I just put the beta sub C, which is the critical point for the graph itself, but of course there is also a critical point for the model inside. And you do you have to go to the critical point, in a certain way to have a model which makes sense in the continuum limit. But ultimately, if you do things properly, you have one of those critical models, like an SLE, the ones described by SLEs, which is living in a random surface, in a way in a continuum which I'm going to describe in a minute. Yes?
The cardinality of G is what? The number of edges of G?
Could be, it could be the number of sites you have here, simply. And of course, linked with the number, there are all of these Euler relations, which you can play with. So just to get, and of course, in the continuum limit, and I'm not going to use this here today, the physicists have, devised a way to deal with these models in kind of field theory-like way, which is conformal. They speak of conformal field theory. So the conformal field theory is the field theory which is described in your model M is in continuum limit. But now, so usually people speak of the central charge, which is one parameter, which is labels which model you are looking at, depending Ising or polymer or whatever, or Potts models. But then here, since we have let the planar graph fluctuate, we speak of the conformal model being coupled to gravity. Before I go to the description of those models in the continuum limit, I want to just introduce two types of critical behavior. So typically, when you are in the plane, when you are on the regular lattice or in the plane, you are going to speak of the critical behavior of some quantities, typically partition functions or probabilities, things like that. So typically an exponent, a critical exponent, will be some exponent x, which actually gives you the scaling of some quantity with respect to a small distance epsilon, measured with respect to a large distance r, for instance, if things are scaling properly. And if you are near a boundary, you will have an x tilde. Actually, you could forget about the boundary exponents here in this talk. So if you are near a boundary, you're also going to measure things locally near the boundary, and you will get other exponents which I represent with the tilde here. If you are in quantum gravity, meaning so quantum gravity, I should have said we are in Cambridge, so Newton, is famous for gravity. Here we speak of quantum gravity. It's a nickname for those models which are kind of toy models of real quantum gravity, because we are in 2 dimensions. There is no time, But what happens is that the metric is fluctuating, as we will see in a minute. So the metric is fluctuating, and so the metric is, of course, represents gravity within the plane, and it's fluctuating, so you call it quantum gravity. And of course, all of these models of random surfaces, originally, even the continuum approach was initiated to try to understand, to have models of random surfaces, but as toy models of quantum gravity. And so somehow it developed by itself, and now it's part, it should be part sooner or later of statistical mechanics in 2 dimensions.
So it's actually, you see the gravity in the metric. It's
yes, it will come, it could come. You will have plenty of pictures. Yeah, it will come. So I just want to describe the exponent. So here we measure things with respect to a small distance, and here we are going to measure things to respect to a small distance or area in the quantum setting, in the quantum gravity setting. I'm going to describe this better later. And then you can, the large distance which you had in your regular graph in the plane will be replaced by the size of your random lattice. So G here was the area of the lattice, so little delta will be a small quantum area. So if you just take this kind of ratio, if this quantity scales with some power delta, we call this delta the scaling dimension, or the conformal dimension, or the conformal weight. I mean, all of these words are equivalent, the exponents also, of the same quantity, but in quantum gravity now. And the aim of the talk actually is to show to you that this x and this delta are actually related. And of course, here just, so this is a typical area of the lattice and boundary length here, if you want to look at boundary effect. I will give you one example of what I mean with those quantities. Take percolation, for people who know percolation well here. Take percolation, so here we are in the plane, not in quantum gravity. Suppose you take your percolation web, and you ask the question, I take a small domain of a small disk of radius epsilon, right? Much bigger than the grid, the finest grid of percolation, and I look at what is the probability that within that domain, I find that domain there is a point out of which you have a certain given number of paths, occupied paths on the percolation web, and also empty paths on the non-occupied sides. So you could ask this question, so you want to have a certain number, the probability that you have L non-intersecting paths, random paths, which traverse, say, the annulus from epsilon here to R. I did not write the epsilon, but the epsilon is the radius of the little disk, right? That probability is going to decay with epsilon going to 0 or R going to infinity in this way, like I wrote before. And this, except that you will have an exponent which will depend on the number of paths you have. Actually, here I put occupied paths in blue and dotted green paths green paths are the unoccupied ones. But so of course this x should depend on the number of occupied, number of unoccupied. But with Michael Eisenman some years ago, I mean almost 10 years ago, we showed that x sub L that depends only on the fact that there are at least one occupied, one non-occupied, and then depends only on the total number of paths. This is just a side remark. It's not part, of course, of the talk. This is just to give you an example of the exponents I have in mind. These are exponents which tell you that locally you have a certain type of fractal behavior on your percolation web, right? And then the Hausdorff dimension of the points, say, where you have this phenomenon occurring, is just given by 2 minus 2 little x. Actually, I forgot to erase this, but this is simply so the Hausdorff dimension in that case of the set of points where you have this kind of behavior. So it's the points on the percolation web where you see a certain number of paths going far away is 2 minus 2xl. So that would be for the L order paths. Okay, so this exponent xl here essentially gives you the Hausdorff dimension of the set. So one knows how to calculate those exponents, but it's not the subject of the talk here. So, and if you are near the boundary, you will have the same behavior. Okay, this was just to give you an example of what I had in mind here. But again, now we are going to have to define the same kind of behavior in quantum gravity. But to do that, I will have to work for a while with quantum measures. Before I go to my main subject, I have to introduce what was done 20 years ago by Knizhnik, Polyakov, and Zamolodchikov. And they actually discovered that if you are on the regular lattice, and if you have a certain exponent x, which I call here conformal weight, but it could be, this is also what I call scaling exponent of conformal dimension, right? This exponent x in the plane, x is in the plane, complex plane C, or if you are near the boundary, that would be x tilde. Then x actually is in correspondence with the same dimension, the same conformal weight in quantum gravity, the capital delta. They are mapped one-to-one by a certain function u, which is this KPZ map. So, and here I just wrote that delta or delta theta is a corresponding conformal weight or conformal dimension or exponent in quantum gravity. Okay. And here I've put Liouville field theory because we are going to address this problem from the point of view of Liouville field theory, which I'm going to describe a bit later. Before I do that, I want to give you the formula. This was predicted by KPZ. So the formula U is a quadratic map. It depends only, so you see x is our scaling dimension in the plane, right? Delta is a scaling dimension in quantum gravity, and the map is given by a parameter, is quadratic in delta, and it depends on one parameter, which here I wrote gamma square because gamma is going to reappear later. And this gamma depends only on which model you have put in quantum gravity. So the gamma will depend on whether you have an Ising model, or you have a self-Odin-Walk model, or you have a Potts model, a Q-Potts model. So this gamma, there will be a relationship between that parameter gamma and the model M.
Well, gamma, it depends only on the central charge?
Yes, yes, it's going to appear in a minute. And the inverse KPZ map is actually just inverse of this quadratic map is given by a square root, which is a conspicuous way. When you see this kind of square roots, it means you have somewhere quantum gravity in action. Because a square root structure like that gives you these quantum dimensions. Okay.
And that would mean that the exponents in quantum gravity will not, in general, be rational, quadratic irrational.
No, usually the fact is all of these exponents you have been floating around, all of these simple ones, which you know, right? They are, which are, rationals. They are rationals which are built in such a way that when you take the inverse, you still find rationals.
But I think remember Philippe Di Francesco had it.
Yeah, but I have even much more than Philippe Di Francesco. Philippe Di Francesco got one for the meanders. The point is that if you look at more refined problems in all of these models, like the multifractal spectrum of, the model and so on, then you are going to find a lot. This is the way I calculate them using this kind of technique. So you are going to find a lot of exponents which are not going to be rational. But what I wanted to say is that the standard rational ones, when you invert them, they become still rational.
This KPZ prediction is based
so the case of Philippe was a bit different, but it was part of this, right?
Yeah, this prediction is based on which hypothesis?
This prediction is based on, there are several ways to do it, but today I'm supposed to give you the rigorous way. So.
Obviously, gamma squared equals 4 is something significant?
Yes, that corresponds to SLE4. The famous SLE4, which is, the most random SLE you get, because after that you go above 4, you get other SLEs which are self-touching. So it corresponds to the critical point of SLE when the SLE starts to touch itself, in those words, right? Okay, so it has been understood somehow in physics 20 years ago, and slowly used, and actually over the years I use these kind of techniques to derive a lot of exponents in the plane because of this map. Because somehow situation is simpler in quantum gravity than in the plane, so there are a lot of things you can do in quantum gravity by surgery and counting dimensions and adding dimensions and everything, and then you project back to the plane where things become much more complicated. But if you know how to handle your random objects in quantum gravity, with KPZ you can go back and forth and derive a lot of exponents with these things. But that was understood, some say, in the physics way, not done rigorously. So with Scott we tried to start to attack this problem. So this is exactly answering your question, Alan. You said gamma is related to central charge. This is the formula. If you want to, so central charge of CFT, if you want to relate it to the kappa of SLE, that is given by the infimum of kappa and 16 over kappa. So this is why gamma equal 2 corresponds to kappa equal 4. Okay, so this is a transparent which actually so also answers partially your question. How were these things understood? They were understood from the point of view that people knew, even so that has not been proven yet also, that these random lattices I've shown you before, when you take the continuum limit, when you take very, very, very large lattices and no longer look at the short distance structure and take the continuum limit, it was somehow understood by Polyakov actually and other people that it dates back from 81, that actually the continuum limit should be description of these random surfaces should be actually what is called the Liouville field theory, quantum field theory, which is essentially, so here I wrote it in a complicated way, but you are on a Riemannian metric, which is fixed here, G hat, and then on this Riemannian metric, but actually you could take also the standard metric, Lebesgue metric, standard Euclidean metric, and then on this Riemannian manifold, 2-dimension 1, you look at the properties of a Gaussian free field, which is H. So you have G, A, B, D, A, H, D, B, H. Then you have possibly a coupling to the curvature of your Riemannian metric. So R hat is the curvature of the background metric, say. But again, it could be just flat if you really want to do that. For statistical mechanics, that would be okay. And then you will have a linear coupling of H with R through a certain coefficient Q, which actually is linked with this gamma. And gamma is gamma. Now the gamma, which I'm going to use later, is a gamma which appears in the quantum area here, because you see the area. So this is your field theory, but now the metric is going to be here. So this is the area term. So this is just a constant here, and then the area is just the integral over your background metric d to the square root of g hat of exponential gamma h, where h is this Gaussian free field. So the quantum area, so the quantum metric is GAB equals G hat times the conformal factor, but the conformal factor of the metric is given by the exponential of the free field. That's a key point. And then you put your parameter gamma here. That's why you put the gamma parameter, okay? And this measure, so this term here, measures the area, weighted by this conformal factor. And so of course integrated here, you just have a constant times the area, so which is your...
I don't understand the interpretation. Is this simply the Einstein action for the metric GAB?
Well, somehow forgot my basics for Einstein metrics, frankly, because I'm working with these ones. It looks a bit like that, yes, of course, because of this coupling here.
I mean, H is not a free field. H is a field with this particular interaction.
Two-dimensional Einstein gravity.
It's given by this kind of, yes.
This is a Gaussian field in the background.
Yes.
But I don't see this Gaussian. I mean,
well, wait.
the third term is non-Gaussian.
This is why the people call it Liouville field theory. It's Gaussian when mu is equal to 0.
Oh, I see. Okay.
Okay.
But so it's a theory of a scalar field.
So now I'm giving you the complete. I'm not going to use it in this way. You will see what I'm going to use, but I'm just giving it to you the complete Liouville field theory, which has a linear part, or quadratic part, which is Gaussian, and then of course, which has what makes the theory difficult is to have this coupling to the area, which is nonlinear and exponential, right? So this is a description of. So if you wish, this is not Gaussian, but the critical Liouville is mu equals 0, and then it becomes Gaussian. So, so I'm not going to use a whole Liouville theory today. I'm not going to use that term nor that term, except that I put it here to motivate the fact that this is going to define for us the area, the quantum area, okay? And and Q, the parameter here, which will reappear later for other reasons. And this typical Q you have is 2 over gamma plus gamma over 2. Yeah. So today what I want to do, I want to simplify things, and I want just to take the quadratic part, the critical Liouville, define this as a quantum area, and look at the properties of what you get when you take this quantum area. Is that more or less clear? And the idea...
So you take the mu A out of the action. You set mu A equals 0, but then you treat e to the gamma h as an observable.
Right.
You treat the area as an observable.
Correct. Yeah, exactly. So random matrix, that's exactly what I'm going to do. So what you want to do is, so this is first a Gaussian free field in 2 dimensions, so it's a drawing made by Scott. So somehow, of course, here it's discretized, and so it looks, so the Gaussian free field is something which is, it's a kind of wild animal because it has correlation functions which are decaying logarithmically, and essentially it's a distribution. So it's something which is not very smooth, and so we are going to take d mu as the quantum area. So we are going to take exponential gamma h times d2z, which is standard Lebesgue measure. So now it takes the Riemannian metric to be just flat, just the background one, right? So I just take my plane. So you take your plane, where you would like to do conformal field theory, but now you are going to let the metric fluctuate by this factor. And so forget about the other details. Now we are going to take this as a definition of the model and see what the result is in terms of scaling behaviors of random objects in the plane.
But as you just said, H is not in general a function. H is a distribution.
Yeah. So you will have to regularize
Is
it.
this Wick ordered, or there's some more complicated regulation?
That will come later. Remember, we want a theorem. So you.
So right now, this is a formal prescription.
Right.
Which you're
Right. But right. Absolutely. Yes. Absolutely. And actually, here it's discretized, so you don't have this problem. But you see, these are domains where you have a lot of area, more area, less area, and so on, which we'll see in a minute. So this is just to give you a hint of what a Gaussian free field is when it is discretized. And of course, if you refine the mesh, it will become more and more wide. Okay, so what does it give you? So that was, so this grid, so you don't see very well, but so this is just a torus, a planar torus, cut into small pieces. So you take this random measure, is discretized. You take this discrete realization of the Gaussian free field, you put it back in the metric, and you look at where the area is on your torus, right? So you just, and then it's just for a gamma which is 0.5, and so the squares here have roughly the same area. So what you say I want an area which would be here actually 2 to the minus 12 times the total area of my set, and so you start cutting your torus in 2. So if one fourth of it has still an area which is bigger than delta, you keep cutting, and when you have an area in your small square which is less than delta which you have prescribed to yourself, you stop, right? And then you put colors. So here these are, so you don't see very well because actually there is structure here which is not resolved by the machine. So I'm going to change the gamma to see more things. And so here you see a little better. So when you have a square here, it means it has this area typically delta. But if you take the blue square here, the small one, it has also an area delta, a quantum area delta. If you take the very tiny ones, which you can't see here, which are black, they are very tiny square, which also have the same quantum area. Because of course the GFF is giving some random weight. So here and there you are blowing up your metric. So you have some small places in the Euclidean place where you have the small quantum area as in large domains like this.
The lines between different colors are just the contour lines of constant H. Is that right?
I'm not sure. I'm not sure. No. Remember, no.
In other words,
No, it was cut. Remember, it was cut. No, it was. You just cut, and it's not exactly. Remember,
no, but roughly speaking.
Yeah, but
the
roughly.
darker regions are the regions where H is high.
Yeah, of course. But roughly speaking, yes.
The steep areas, right?
Yeah, but you give, remember you cut and then you divide as long as you are above delta. At some point you just stop when you're below delta. And of course it will be mostly, so it will not be exactly delta or, it will, so you will have some, of course, some
This cutting
fluctuation.
thing, is that part of your construction?
No.
It's just something you're doing to show this?
Yes. Yeah, this is why you should not, actually,
So,
I should give you a warning that is not, of course, the key point.
Right.
So,
what's really
could I?
relevant is just the contour lines of constant H.
They look a bit like that. So anyway, yeah, probably, yes.
Where H is high,
Yeah.
you have
More precisely, e to the gamma h, h of x, volume of the square within x, is more or less delta, isn't it?
Yes.
If it was larger than 2 delta, you would have.
Yeah, but of course, I mean, it
So
should. But
H
I'm not going. Yeah, right.
Log h is between.
I don't want to go into those details because it's not the way. It's not the way to address the problem. It's just to give you a picture, give you a feeling of how it looks like. And actually, I'm going. So this was gamma equal 1. and gamma equal 1.5, because the more gamma, the higher gamma, the wilder it becomes. And then you gamma equal 2 becomes like that. So you have zones when you have essentially no quantum area. You need a large patch of Euclidean area to see a given small quantum area. And then, of course, it's concentrated here and there. Okay, so just to give you an
Gravity without matter is gamma equal to?
gamma equal 2 without matter. No, that's
No,
couple.
equal to it was TO. Which gamma corresponds to pure gravity?
Gamma equal, let me see, pure gravity. But it's a bit irrelevant to what I'm describing here. Gamma equal, that I don't remember, is C equals 0. That's kappa equal 8/3. So this gamma is, yeah, so you see. You should put C equals 0, so it's kind of 5 minus 1, so 4 divided by square root of 6.
So it's not
Not-
a trivial value.
No. But no, not here. Okay, so let me move on because I think it's not finished. Okay, so Gaussian free field. So now I want to, exactly as you anticipated, I want to rigorize the model, but not with a discrete Gaussian free field on the grid, which of course you will probably like to do, from a rigorous point of view. But we are going to take a continuum limit. But to take the continuum, you are going to look at small domains and take the average of the Gaussian free field on small domains. Actually, and more than that, so this was just a recollection of the picture which you have in mind. So before I go to the regularization, I just want to define a few things. So it's not very, I've put, as the least equation I could. Of course, there are some, but essentially it will be electrostatics in the plane. So you will see formula, for the beginning, you will see formulas that you have seen, in many places. So remember, so the weight will be a Dirichlet form, which will be essentially something like HH gradient, so which is an F1, F2 gradient, is just, the integral over the domain. You take a finite domain. You will take, to simplify things, I'm going to take Dirichlet boundary conditions for my fields, and I'm going to take the Dirichlet inner product in the domain D, which is given by this, okay, for two functions or two distributions. So, and then the Gaussian free field will be defined by this weight. And then if you take the covariance of H, so just a little lemma, which might be useful later, but it's not, so all of this is kind of very well known. If you take the covariance of HF1, where F1 and F2 are two functions, so if you take covariance of HF1 gradient, HF2 gradient, integrate over H, you are going just to find the Dirichlet inner product of F1 and F2. So just to define the model. Now, what we are going to do to rigorize the problem is to take the Gaussian free field and take its mean value on a small, not on a small disk. It's simpler to take it on a small circle. So take a point Z in your domain D. You take a point Z, and then you take a small circle of radius epsilon. So keep this epsilon in mind because epsilon will stay there up to the end. So you will have a small disk of radius epsilon, and you take the mean value of the Gaussian free field on the boundary, meaning that H sub epsilon of Z is just the integral, so H rho is in general the integral of H of Y, H rho of Y on the domain. But as a density rho, I take rho, the density which is just the Dirac measure on the small circle. Right? So this is Dirac measure on the small circle. You integrate over the circle of radius epsilon, centered at Z, and you just integrate H with this, and that gives you, and you divide by 2 pi because you have integrated here. So this H sub epsilon of Z is really simply the mean value of the Gaussian free field on a small circle.
There is any continuity or possibility of making derivatives in epsilon, or it changes dramatically from epsilon and epsilon plus the epsilon?
You will see that. I will tell you exactly what kind of stochastic object this is. Actually, no, it cannot be differentiable. It's not differentiable. But you will see exactly what it is, because we are going to look at the property of this guy, actually. Okay, so I'm sorry because I realize you. So remember, now we have for the next slides, the next slides will be actually electrostatic slides. So So you will go back to your basics of electrostatics. And remember that rho here is just a density on a circle. So now look at the potential which is generated by density of a circle, the Newtonian potential, so which is a proper place to do. So if you ask what is the potential, suggest minus Laplacian of the potential is a density, that potential is given by that formula, because the density is just density. It's like the sphere in the space. It means the potential becomes constant within the circle, and so the potential is simply given by, so it looks like that. It's a logarithmic potential, essentially, but when you reach a circle, it becomes constant. So the potential is essentially the minus the log of the distance to the center, but when you enter the disk, your distance, you become constant. So the potential raises like that, but when you go at the distance epsilon, here, you just cut the potential, it becomes constant. So it's a log cut when you enter the disk, okay? So it's minus log of the max of the distance to the center and epsilon. But of course, if you have a domain, you have to correct for the existence of a boundary, right? And the fact that you have the existence of the boundary means that you have to correct, so you have a certain function which takes into account the fact that so this is just the harmonic extension. So it's a harmonic function which has value minus the log on the boundary, and which is harmonic, and so you subtract it, so it means you have zero boundary conditions. So this f has zero boundary conditions, okay?
It would be the same if instead of having Dirichlet on a boundary, you would have a manifold with a number of handles, something like that, with not boundary, but with...
Yeah, but, right. But, yeah, you could do, of course, you can, this is just electrostatics in 2D, so you can generalize everything you want. But this is not really relevant to what I want to do, because actually, the whole business of the KPZ will come from the short distance properties of those potentials. So it's not linked with the fact that you have boundaries and the boundaries are Dirichlet and so on, of course. You see what I mean? I'm just taking things into account because I want to have something which is well defined and neat. But the key points will come from the stochastic properties of this field H sub epsilon of Z at short distance, at short epsilon.
In the back.
Yeah, right. Okay, so maybe we should make a pause because I understand this is after lunch, so everybody gets very tired. So and I'm not yet at the end of my talk, unfortunately. So so I just want, so here this is just electrostatics. This is a potential associated with a density of mass or density of charge on a small disk, on a small circle within a domain. Okay. So, but this function somehow will play an essential role almost up to the end. So that's why I insist on this structure. And sorry, it's the wrong one. Well, this somehow is a bit technical, but the green function in a domain like that. So this again is just electrostatics. The green function is defined here. So define the regularized green function like the covariance of h sub epsilon of y, h sub epsilon of z. So you take your mean Gaussian free field on two little circles and look at the covariance of this. So integrate over h. That gives you the green function, which is regularized. So it has a lot of nice properties, which are the fact that this green function is the full green function independent of epsilon as soon as the distance between the 2 points, as soon as the two circles are not overlapping. Okay? And the second property is that when you now, since you have regularized your field, when you let y and z approach each other, you no longer have the standard logarithmic singularity, but you hit a log of epsilon because everything was regularized. So this g of sub epsilon of z, when I take y and z equal to each other, is no longer minus infinity, plus infinity, it's minus log of epsilon, plus something depending on z, which was my harmonic extension of the logarithm. And so it means, and so it's just something which is the log of what is called the conformal radius of the domain. So what I just want, but you don't need these details, just to make things finite and nice if you calculate everything. But the key point is that you have this regularized green function, which is defined like this, which is a full green function at large distance, but at short distance, it's just given by this kind of behavior. This is not an essential, this is not essential really just to make definitions. So now if you take So now I'm really doing things which are elementary. If you take a Gaussian random variable with mean A and variance B, the expectation value of the exponent of EY is just e to the mean A plus 1/2 of the variance, right? A standard result of Gaussian variables. So the mean of exponential y is exponential A multiplied by exponential B over 2, where B is a variance. So of course B is quadratic typically. Okay. So now if I take my Gaussian free field, so remember I take my Gaussian free field, I regularize it by taking its mean on a small circle. So it means I have h sub epsilon of z. Remember, the epsilon is essential here. It really means the Gaussian free field on a small ring. And take the expectation with respect to the Gaussian free field of this. Then you find simply, so there is the mean is 0 because you have Dirichlet boundary conditions. So the mean of h is 0. But you have the variance, and the variance is just what I define here at coinciding points. G sub epsilon of zz, meaning that is this, right? So because of this formula, you get epsilon gamma square over 2 of G epsilon zz. And if you put now the formula I had before, which was G of epsilon at coinciding points equal minus log of epsilon plus log of c, you find this nice formula. Okay? Which of course is not yet quantum gravity, but already tells you, what is the expectation value of this regularized quantum factor, at around a given point. So it depends on the distance to the boundary because by the conformal factor. But more importantly, of course, you see it blows up when epsilon goes to 0. Because when you let the epsilon go to 0, of course, the metric fluctuates more and more widely, and thus your exponential blows up like that.
And also it blows up with an exponent which depends on gamma, which is nice because it is really the dimension, fractal dimension.
There is more than that to come. There is more than that. So you have something like that. So to define properly the metric, you remember before formally I defined the metric by taking exponential gamma h. But if you want to define it properly, you should take exponential gamma h sub epsilon and multiply also by epsilon to the gamma square over 2 in such a way that when you take expectation, it is finite. Okay. So lately, when I will define properly my quantum metric, I will put, you won't see it probably because you will be somehow lost in the details, but it's typically I will take exponential gamma h sub epsilon, right, as a conformal factor, and also multiply by this factor epsilon to the gamma square over 2 in such a way that I will have a nice limit. Okay. Well, this is just preparation. Well, now about your question before. You ask what are the properties of this h sub epsilon, okay? H sub epsilon actually is a Brownian motion in time. And what is the time? The time actually is the logarithm, t, the time is minus the logarithm of epsilon. So this transparent is somehow a key point. The circular average of the Brownian motion, right, along a circle. So denoted by hd is the average value of h on the circle db epsilon, of radius epsilon, center at z. Write bt like h of epsilon, where epsilon is exponential minus t of z, right? So in other words, t is minus log of epsilon, right? Of course, the point is that you also have to have your circle small enough in such a way they are within the domain. So this t sub 0, this epsilon 0 of z, is just the biggest epsilon, is just the biggest radius you can have. So all the radii should be smaller than the one which is at the boundary here. Otherwise, of course, you cannot take the average. This is just a remark. So essentially, as soon as epsilon is small enough, so the idea is to have epsilon going to 0, to shrink your disk. So as soon as epsilon is small enough, okay, you enter the disk, you take your average, and then your h sub epsilon is a Brownian motion with respect to minus log of epsilon. I'm sorry.
In the sense that
so this b sub t, taken at time t plus the minimal time you need, minus b of the minimal time, this expression is a Brownian motion in time. Exactly.
So the difference are okay, but of course the offset is totally free. You would have to fix it somehow.
Which offset this?
The offset of the Brownian motion, because
what do you call the offset?
Starting from 0.
No, but yeah, right. Yeah, but that.
You don't know where it is starting from, because in 0 it's simpler, and on the.
Well, you can start from BT from this one. start from this one, and then you have a Brown motion.
Well, it's a
Well, I understand your point. But let's
epsilon at any value of epsilon.
well, we won't need it probably. Okay. So, well, I have a proof of this, but considering that everybody looks very tight, I might skip the proof of the fact that it is a Brown motion.
One person just woke up.
Yes, I know. Yeah, but that's good that at least one person is waking up. So the proof of the fact that so it's a key thing that this GFF on taken on a circle is a Brown motion with respect to the minus the log of the radius. This is a key point. So if you admit it, so the proof actually goes with using this covariance and so on. So it's not difficult. I'm going to skip it. I had all the operators to prove it to you, but there are more difficult things to come. So random matrix. So the thing is that so now suppose we are going to take we are going to sample Z from its marginal distribution, which is the expectation of gamma H sub epsilon d to Z, which we calculated before. You sample it from its marginal distribution. Sample H from the distribution of Gaussian free field, weighted by the famous factor we wanted, exponential gamma H sub epsilon, right? Then the statement is that the later, the GFF, weighted by this, has a law of the standard GFF, without this weight, plus a deterministic function, which is this famous potential, this famous logarithmic potential of the disk. This gamma times Fz of F in the Fz epsilon, the circle potential we have seen before, okay? So I'm going to show you this to you in a minute, so this is not difficult. So remember, so this is simply taking Gaussian, which has a linear term, and completing the square of the Gaussian, but doing it properly here for this setting. So remember, we have our density on the circle, which is the potential F, the logarithmic potential, which is the potential of the density. Remember, the mean GFF is just integrating H over the density rho of the circle. Use the fact that rho itself is the Laplacian of F. Just do standard tricks. You are going to find it is a Dirichlet form of H with a potential, okay? And remember also that the green function regularized with epsilon is also the Dirichlet form, something I've not shown to you because I did not do the demonstration of the Brown motion, but easy to show by using this, that remember G of epsilon is the covariance of the regularized field, okay? So now and each one is the Dirichlet form of H with the potential. So it's not difficult to show that the covariance of the GFF is given by simply the Dirichlet form of the potential. So you see, this H F sub epsilon is a Dirichlet form of H with the potential. The green function is a Dirichlet form of the potential with itself. So this is very useful because now look at this combination, standard Dirichlet form for the GFF, minus the shift which will come from this Liouville term. Remember, the famous Liouville term, exponential gamma H. There will be a shift because when you will be in the exponentials. Because remember, you want to compute something like that, right? A weight. So I want to compute something like that. So I'm looking at this first. Look at this. So write it, just do the expansion, write it H minus gamma F in the Dirichlet form, and then compensate for, so this term here is generated by H, so F, you have FH, but FH, the Dirichlet form is H sub epsilon, so this term here is just the non-diagonal terms of H and F epsilon, and then you have an extra term which is gamma square F of epsilon square taken in Dirichlet form, which I subtract here. Is that clear?
Is it correct to say that this is also an approach to the longly expected way of making renormalization group, in the sense of coarse graining of short distance degrees of freedom?
If you wish, so yes. Yeah, of course, yes. In a way, yes. That's a continuum, starting from Liouville field theory, yes. Not starting from the discrete lattice. But that's a way to do it, yes. So you have this form, so you see it's this. Now you define H prime as H minus this deterministic potential, and you find that your weight here, with this linear term is simply the standard GFF weight plus a constant, which is this regularized, because this FF is also the green function. You see? So accept this in a minute and look at what it gives in terms of weights, of statistical mechanics weight. So you want, this is the weight of the GFF, this is a Liouville weight you are going to have in your quantum measure, right? You just use what I said, use the fact that this is the same as this, and you rewrite it. So this is just completing squares in Gaussians. So you have this nice Gaussian weight, and then the constant term. And the constant term itself, it was just the expectation of exponential gamma h. So you see exactly what I said. You said that the weight, the Liouville weight for quantum measure, weighted by the Gaussian free field, right, the Gibbs weights, are given by the Gibbs weights of a standard GFF multiplied by the expectation of this measure, you know, which is given by this formula, which is under control. So meaning that your h in low, so this is just written in terms of in low. So the low of h with this weight is the same as the low of h prime, because remember I wrote h prime equal h minus this. The low of h prime, which is a standard GFF, plus the deterministic potential, which, you know, I insisted from the beginning was important, because this deterministic potential is given by this form here. Okay. Well, so now we are in beta sitting, because somehow, so we have two ingredients. We can use a standard GFF. We know the shift, and we know in addition that this h sub epsilon is a Brown motion. And then you can do probability theory. So this is, I'm sorry, it's a bit complicated. And here I just recall you what this shift here, this shift from the standard GFF is. This shift is just given by this, which is this famous logarithmic potential here, which we have. And remember that if you shrink your domains, you know, you just go higher and higher. And remember that the epsilon going to 0 is minus log of epsilon is the time. So when you shrink, you are just going higher and higher in time with your Brown motion. Okay. So shrinking the domains is just letting the time run up to infinity. So I'm going to the last part. So the quantum area in KPZ, because I want to show you the KPZ formula ultimately. So I have to define quantum areas. So I'm going to do exactly what I said many times. I'm just going to do it better. So I'm going to take a small epsilon ball. Remember, so I take a small ball, and I'm going to define its quantum area by, now we have understood better the structure. So I'm going to do it by the famous exponential gamma of epsilon sub z, h sub epsilon z, and then I will add exactly what I need. I will add gamma q. Gamma q, remember, q was written like 2 over gamma plus gamma over 2. So gamma q is simply 2 plus gamma square over 2. So this gamma q here, log of epsilon, is simply, remember, this is the exponential of this. So this is really epsilon to the 2 plus gamma square over 2. Okay? I should write it here because it's not very clear, perhaps. This term exponential of gamma q log of epsilon is really simply epsilon to the square plus gamma square over 2. Okay? And the epsilon square here is just the Euclidean area of the small ball. I don't take the 4 pi into account here. So this is just the Euclidean area. And this epsilon gamma square over 2 is the extra factor I want to put to make sure that my measure is defined the continuum limit. Remember, I explained to you that you had this extra power of epsilon to the minus gamma square over 2 popping out, so I put it there to regularize things. Okay? So it means that I redefine my delta like that, such a way that it's properly, it's supposed to have a continuum limit. Okay? Now, what you are going to define something else. So this is the quantum area. So the area of the epsilon ball is epsilon square, but the quantum area is exponential of gamma h times epsilon square times epsilon gamma square over 2. Okay, defined like that. Now, you fix a delta. Delta will be, so you will have two quantities. There will be a Euclidean quantity, which is epsilon, and there will be a quantumic quantity, which is delta. Epsilon square, so delta is an area. So delta is like epsilon square modified by the GFF. So the delta, when you see a little delta in green, that means a quantum area. When you see a small epsilon, it means a Euclidean radius, right? And so you call B tilde delta of the largest Euclidean ball for which this area is equal to delta. Because this area, of course, you know, is stochastic. So you start shrinking your domain when your epsilon is such that the delta for a given realization, delta, you reach delta. You call this B delta. Okay. So you refer to this as a quantum ball with area delta.
If you add the geodesic on the true random triangulation,
No,
it will be more or less like delta or like square root of delta or like epsilon.
It should be square root of delta, I guess. But that should be. No, not here. You will see. But yeah, you hope. Yeah, you expect this to be square root of delta. Yeah. Okay, so now I'm almost finished. So for people who feel the courage to try to follow the last transparencies, you are going to have. I'm sorry, it looked technical, but if you think about what I did, I just did standard Green's function theory in any domain. I just did regularization of Gaussian free field. I just completed the square of a Gaussian, which is, you know, of course, in a nicer setting than usual, but still it was completing a square. So I've not done much. But there was one thing I told you which I did not prove, but because I thought it was a bit too much. But I said something which is key, which is that the mean value of the GFF on a small disk, on a small ring, is a Brown motion. And once it's exactly a Brown motion. So, I mean, in the continuum. So once you know it's a Brown motion, you can use that property. This is what is going to be used in the large deviations, because remember that in the title there was large deviations, and the large deviations are going to be used simply of this H sub epsilon, namely the mean value of the GFF on a small ring.
And the reason you care about large deviations is because it's exponentiated.
Because KPZ is a large deviation result, actually.
But because it's e to the gamma h that you care about.
Yes, you can see that, but I'm going to do it in detail now. So remember, at the beginning of the talk, I gave you examples of fractals, saying that remember I explained that the house of dimension is linked with the scaling exponent in the plane like that. Remember that? And so essentially, so if you have, now I'm go back to my random fractal. So I suppose I have percolation. Suppose I have a self-reading walk. Take a random fractal in the continuum. And you are going to say, so X will be the random fractal. You know, the ones I've seen before, you remember, long time ago. But, sorry, I did not spare anything to you, but this kind of objects, say, right? So they had a certain exponent X, and I said that this house of dimension of the fractal is given by that, for the local behavior, say, for instance. Bon, okay, so I go back. So it could be, if you wish, if you want something definite which is less complicated than this path, take a percolation web and say that your fractal is just a percolation cluster. Take a small disk, look at how many points you have there. You know, you have certain fractal dimension which is 91 over 46, if I remember correctly. So that gives you a certain exponent. It means that the probability that if you take a small ball of radius epsilon, look at the number of points which are occupied in your percolation cluster, right? So you look at the intersection of the ball with the fractal. The probability that this intersection is different of the empty set is going to scale with the size of your disk with some epsilon to the 2x. And this x defines the house of dimension, okay, as before. So we are in the Euclidean plane, standard plane. Okay. Now you want to do this in quantum space, in the quantum metric. So you are going to define a quantum conformal dimension of delta. Remember, in the KPZ, I introduced this x and this delta, saying that they are related by this KPZ formula. So now I'm going to define a bit more properly using my GFF. So you said that the quantum conformal dimension of x is delta. When you sample h and the point, and x, the random fractal independently, you sample them from the quantum gravity measure, which we have seen, and from the law of x. And then you are going to say that the exponent is delta if the probability that this quantum ball, the one which has quantum area delta, remember, this B delta here is the one which has the quantum area delta defined by this, okay? So your ball here, your quantum ball, the one which has quantum area delta, the probability that that ball intersects X, okay, that probability scales with the quantum area like a little delta to the capital delta. And that is going to define my quantum scaling dimension. Okay? Just here you use the standard You use standard Euclidean metric. Here you use just a quantum metric. Okay. So theorem, x and delta are related by the famous KPZ relation, which is given by x equal gamma square over 4 delta square plus 1 minus gamma square over 4 delta. Namely, where of course gamma is the gamma I have put here and here. So as simple as that, right? So how do you do that? Large deviations of the Brownian motion. So remember, so there are, I think, 3 slides, and you should be done.
You mean you do that without using KPZ paper?
Of course not. We want to prove KPZ.
Ah.
That's the point. So that I'm going to. So actually, these are 4 slides. So maybe if you. I'm sorry, but so there are 4 slides, but somehow what I explained before will tell you exactly why everything works. So remember, given a point z in your domain, take the mean field on a small ring. Okay, it's standard Brownian motion with respect to t, where t is minus log of epsilon. Something I'll ask you to accept. Then plus, but you remember that the h weighted by the Liouville factor is the standard GFF, namely standard Brownian motion, plus the deterministic function, the famous f sub epsilon of z. Right, that's what we have seen. This function, remember, was starting with minus log of epsilon at short distance, which is the only thing you need really. So if I have gamma f, it is minus gamma log of epsilon, which is gamma t. So it means that h sub epsilon of z, when you take the Liouville measure, is just standard Brownian motion plus a shift, which is deterministic, a shift in time. It's a shift which is completely in terms of z, but in terms of the time, is simply plus gamma t. So remember, this was our quantum measure. It was exponential gamma h sub epsilon plus gamma q log of epsilon. Remember, it was defined like that. Now, say h sub epsilon is a Brownian motion plus a shift. So it means I replace h sub epsilon by bt, the Brownian motion, plus gamma t. But I had a gamma, so I have plus gamma square t. And then this gamma q log of epsilon, it is minus gamma qt, where t is minus log of epsilon. So now you have, so in terms of the time and in terms of the Brownian motion, now we have the quantum area, which is written like the exponential of a Brownian motion, plus a shift, plus a drift here. Okay? But of course, if you have Brownian motion plus drift, probabilists know exactly how to handle these animals. That's well known and easy actually. So we are going to see it. And I will just recall you that gamma was, Q was defined in terms of gamma like here. So now, remember the idea to define delta. You take your big Euclidean ball, start to shrink it, and when the area, you give yourself a little delta, very tiny delta, which is quantum, and when your ball reaches the level epsilon such that the quantum area is delta, you stop. So the statistical area of the ball equals delta at a certain stopping time. Stopping time is t minus log of epsilon, a certain epsilon, if you wish, such that minus log of epsilon, which is the time, is the smallest time for which this quantity here reaches a certain value delta, for which you have equality here. But if I take the logarithm, you can write this equality as minus bt plus q minus gamma, because this equal minus log of L delta over gamma. So that equation here is just this identity here. That's the same. Okay? And this time t, the stopping time, is just the smallest time for which you have the equality. Okay?
But still you need an origin for the Brownian motion. A Brownian motion.
Yeah, understood. I understand. I put the question aside. I want to finish that. Okay, understand that. So you have minus log of delta over gamma, right? And now you look for the smallest time for which this combination equal to this, and I call that element, which is minus again, which is minus the log of the quantum area divided by gamma. I call it A. So I'm in a problem where I want to see what is the smallest time for which a Brownian motion. We're actually, yeah, but you see, you can shift your Brownian motion. You can define it from you start with epsilon 0 and that.
Exactly. If at epsilon 0 the Brownian motion starts at some x0, that's fine. The problem is that we do not have a value for epsilon 0.
Well, okay, let's keep it later. Okay. So I want to finish this. So I want to reach the level A. And okay, so this is just a large deviations lemma for Brown motion. If you ask the question, what is the smallest time for which a bt plus at reaches a level A? If you define the variable ta like 1 over a, you have to do the proper scaling. Take a is large because delta was small, so a is large. So ta is just this time rescaled by a. And little a is fixed, okay? So the random variable satisfies large deviations principle, namely that the probability that ta is equal to eta is simply given by exponential minus a times a rate function I sub I of eta when a goes to infinity, here, the level you want to reach, right? Where this rate function is simply given by this expression. It depends on eta, your variable you want to give to ta, and it depends on a little a, which is here, and it's just, apart from that, it is well defined. So the way to prove it is just to rescale things and look at all functions satisfying phi of 0 equals 0, and then you look at this problem, phi of t plus at equal 1, and you look at such a way that eta is the smallest time for which you do that, and the function which does this with which gives you the rate function is the one which has a minimal Dirichlet energy, so meaning the minimal of this functional, which you have seen, of course, in the thesis way of writing the Wiener measure. So if you do this, if you solve this problem, it's easy. You want to reach a certain level at a certain time, eta, you just go straight and then you stop. So, and if you take this function is given by 1 over eta minus a times t here, and then it is constant here. If you calculate is, for this function, is Dirichlet energy, you are going to find this equation I put here, okay? So that's an elementary exercise in Brown motion calculations, stochastic calculations. So this is why I said, so I repeat here, the ta, which is 1 over a, the inf of t, such that you reach the level a, has a probability distribution, which is a large deviation formulae, which is exponential minus a times a rate function given by this. But remember, eta is the value you ascribe to ta. So you say, what is the probability that this ta is eta? This probability is minus a times this function of eta. Large deviation.
TA means equal to eta. I mean, being a little imprecise. I mean, it's not going to be a discrete distribution.
It's not discrete, it's continuum here. But it's a large deviation principle, right? It's a large deviation, so it just scaling like... yeah. No, of course it's not, yeah. Okay, now I'm going back to my question. Remember, so this was just a lemma. Remember that what do we have? We have, sorry, this is what I want to do here. Right. We are in the Euclidean space. We have epsilon to the 2x. In the quantum space, we have b tilde of delta, which is the corresponding quantum ball with area little delta, quantum area. This probability of intersection with x should be scaling like this. I want to compare these guys. Okay. So that's what I'm going to do it now. So remember, delta was defined like this. So written in terms of the bt, and we wanted to reach delta by this stopping time here. And I just looked at the probability that this equation, this stopping time would be equal to eta, getting this rate, okay? So now I'm going to use this. So rewrite, so choose ta as above, then consider the quantity epsilon to the 2x, which is exponential minus 2x ATA, because you probably don't see it, but ATA here, if I put ATA is the inf of t, and inf of t was my minus log of epsilon, okay? So I can rewrite this as this. So consider this quantity. Now you know the probability that t equals eta is given by this large deviations principle. So the expectation of this quantity will actually be given by looking at the maximum value of this quantity multiplied by the probability. That means it will decay exponentially in A as exponential beta minus beta A at rate beta, where beta and x, which was here, are related by Legendre transform, because you just combine this one, make a convolution of this one with this one. So you look at the Legendre transform of the rate function plus 2xa, which was 2 each ta, and ta was eta here. because A is a factor, which is here, and which is here. So you have A here, A here, A here. But here you have TA, which is eta, and you have minus 2x eta, and I of eta. And so you just take the beta, which is the infimum of this, so which means Legendre transform. You do this, and you find beta here equal to a square, little a square. The little a, remember, was the one which was here, so which was in the rate function. So you have little a. Then you have your x, because you have given yourself a given x. You have taken a given fractal with a certain x. And then you have this relation once you take the Legendre transform. Now invert this, and you find that 4x is equal to beta squared plus 2a beta. Okay, so this is almost KPZ. So I still have one slide to have KPZ. So x, remember, x is simply the exponent which you have in the Euclidean world. Beta is the rate of the exponential decay with a of the exponential of 2x, right? When you condition to have the quantum measure delta, which I'm going to use this in a minute. And a, remember, was just the a I had here. Now go back to the problem you had in quantum world. The quantum world, you had minus log of epsilon, inf of t, so minus bt plus this. So this was a, this was little a, the drift, and that was capital A was minus log of delta over gamma, right? So put things together. That's the last transparent. Okay, this is so KPZ at last. So remember, we have t minus log of epsilon, which is ATA, which is this infimum, and this little a. And my capital A is this one. Okay, just recollect things. So you describe the quantum probability that your quantum ball intersects the fractal set X. You just sample the radius of epsilon of the ball B of the Euclidean ball, which is the same as this one, such a way. So you sample it, and with a delta, and you assign the probability, the fractal Euclidean probability, which is this one, right? And then, so you are exactly in the setting that we have seen before. And so the probability that the quantum ball intersects the fractal is scaling like exponential minus beta a, right? Which we have seen. But remember what a is. A was minus log of a little delta over gamma. So you plug this here. So you replace a by little delta. You find little delta to the power beta divided by gamma. And you call beta divided by gamma, you call it capital delta. And you remember that we had this relationship with beta. So now you replace little beta by delta, which is just a factor gamma, a trivial thing. So and little a was this term here. This was 2a, 2 little a here. And so this is x, 1/4. You replace beta by delta over gamma, and you get KPZ. I'm sorry, I made things a bit complicated because I wanted to give you all the details, but it's not minimal. I could probably simplify the way to do it. But essentially, you got the derivation. So you see, this is a famous KPZ.
Is this how they derived it?
No, this is how we derived it, and which is not published.
Let me ask you a conceptual question. If I understand correctly what you did, you have some statistical mechanical model, some random fractal model on Euclidean space. It gives you some random fractal capital X with some dimension little x.
Yeah.
Then you independently choose
Gamma. This is a...
No, gamma's enough. Gamma's enough. So on the one hand, you have a process that gives you a random fractal on Euclidean space.
Mm-hmm.
On the other hand, you have a process that gives you this random function h,
Right.
Which is just a Gaussian free field.
Right.
And then you put them together by imagining that you deform space by some factor e to the gamma h.
Right.
And then you compute this quantum thing.
Yeah.
But is that the right thing to do?
That's
In
one way.
gravity, you have independently the random metric and the matter field, if you want.
But if you look at the
matter field,
when you look at the way people do quantum gravity with the Liouville field theory, they have this Liouville field theory I showed you before, and then they put another operator, which is integrated over the space, and somehow this operator is supposed to describe this random fractal. But of course, the the H is not the operator they have put, so that's a new operator they have put.
No, what I don't understand is isn't this, let's say that our random fractal is item correlation.
Yeah. Now, there is one thing which you have not, which somehow is close to what you are looking at, but something which surprised us here with Scott is that we wanted to, it's part of the whole picture, because I said in the talk that in CFT, when you put a given model on a random lattice, you know that people believe that you go to the Liouville field theory with a certain gamma, where gamma is related to the central charge of the model you have chosen. Okay, so there is a kind of interplay between the gamma, the Liouville field theory, and the model you put on it. Okay, while here, this approach we have chosen here to derive the KPZ, in that approach, our gamma is independent of the fractal we have looked at. And if you have looked at the way I did it, I just need scaling. I did not need conformal invariance.
No,
so in a way, no, wait, let me finish. No, but you don't see the point. In a way, this is very robust. So there is something which was somehow unexpected, that we find KPZ here with a gamma which is a free parameter, which is not the gamma which is necessarily linked with the model we have in mind. So if you ask me, I take percolation. So for percolation, there is a certain gamma predicted by the KPZ, the gamma in terms of central charge, which is one which has nice conformal invariance properties altogether, but somehow you can partly decouple them and nevertheless still have KPZ formula, because the gamma here was a free parameter. Right. You see? So it's even worse than what you think.
Okay, so what I'm trying to, you've shown, as you say, that you can take independently, you take two independent realizations. You take an independent realization of the fractal model, whatever it is, with the free field. And as you say, gamma is an arbitrary parameter, not necessarily related to the fractal.
Right.
And then you put this stuff together and you
then
get something and you say what its scaling dimensions are. But that's not the original quantum gravity problem, is it? I thought the quantum gravity problem...
What is a quantum gravity problem?
Well,
there are many ways to...
I thought the quantum gravity problem that people are interested in is they make a coupled model. Let's say the model is the Ising model, right? They're interested in the Ising model coupled to quantum gravity.
Yeah, but...
So the Ising configuration affects the quantum gravity.
That's exactly what I said. So then you get a gamma which depends.
But how do you know that?
So how do you know? First of all, nobody knows how to make this quantum standard approach rigorous. Nobody knows yet how to derive from these discrete models, Ising on top of a random lattice, to take the continuum limit and go to the Liouville field theory. So if you believe that the limit is the Liouville field theory, then you should find that your gamma is linked with the model, the Ising model, right? Here we decouple this.
No, but I have a worse problem. I don't see how your construction with any gamma should give an answer to the quantum gravity question.
Right?
Whatever your gamma is, you have independent fractal and metric. Whereas the quantum gravity problem is fractal coupled to metric.
But your question applies to the Liouville field theory.
Well, I don't understand much about the Liouville.
Yeah, but so your question applies to Liouville field theory.
Because the Liouville theory is a theory of the metric alone?
Yes.
And so there's some argument...
Yes, that's exactly the point. That's the whole point. Because you think, you have a tendency to think in terms of the lattice approach. I think things are being coupled. So indeed they are coupled, because the remnant of this coupling is the fact that gamma is linked with the central charge. But apart from that, you have a Liouville field theory, which is coupled to the CFT. So the CFT is a CFT. You couple to a Liouville field theory, and these two guys live together.
Well, what's the couple? I don't understand. What's the coupling?
Well, the coupling is you have to put extra terms, which I did not write here. You have to put extra terms of you have the Liouville field theory, you have the action of the CFT, and then you have terms which are coupling both of them. So you have to integrate your operators of just in the loose way that I like physicists like to write things. So they would just take one operator, phi field, say your Ising field or whatever. They would integrate it over space with the Liouville factor, my factor, exponential gamma h. Okay, that would be the coupling. But you will have one action for the CFT, the standard one, and then you will have the Liouville action in addition to it. And these two guys will be on the same Lagrangian, but as two dynamical parameters. Coupled via the metric only.
But then
Coupled the way we just couple them here.
I don't see this coupled the way you coupled them here. Your things are not coupled. You took an independent realization of, let's say,
wait, come on. When I take a Gaussian free field, take two variables x and y, I put in the, so you have one term which depends on x, one term which depends on y, and then you have a term which depends on x and y. This is what you call coupled. So so if I understand what you would like to, you would like to, understand what you would like to do.
Let me just say it again. Your construction took a probability space, which is a product space. You independent, I mean, imagine you're doing this on a computer, right? You independently generate a configuration of, let's say, the Ising conformal field theory on Euclidean space. Independently of that, you generate a Gaussian free field. And then you put them together in a certain nonlinear way. And you compute the law of what you got. But if I write an action that couples two fields, it's not usual that the law of that coupled action can be gotten from the law of two independent things by a simple nonlinear transformation. Is there some reason to
This is
believe?
what is happening here. This is the whole content of KPZ.
Is that what KPZ is saying?
Yes.
This
is the same.
I mean, I think you don't know KPZ very much because, so that's exactly the point. So they have been related to one to another now, the two behaviors, this way.
So the point is the coupling between the conformal field, let's say Ising, and the metric.
Look at
such a simple form that you can reinterpret it as two independent ones pass through a certain nonlinear transformation.
But look at the look at here when you do the Legendre, right? You have your coupling here. This was just a result from the pure Brown motion. This was what you put as an input of your theory, and you find that there is a certain rate which is depending on x. So it's depending on which thing you have put.
No, you're not answering my question, because here you've already defined what the quantum experiment was.
I think we should give a break to our colleagues. I think it's really 1 hour and a half already. So.
I mean, it must be, maybe KPZ answered my question, at least non-rigorously. I mean, in general, if you have a couple, just consider a coupled field theory with two fields, phi and psi, with some action that mixes phi and psi, right? There's no reason to believe in general that you can generate a realization of that by doing something independent, by doing two independent things, one for phi and one for psi, and then mixing them with some nonlinear map.
And what,
not any simple nonlinear.
Not just the independent ones. The one for psi, say, which is the h, as a parameter which is being shifted by phi.
I think
the gamma is being raised from pure gravity to pure gravity plus.
I know, but even changing, even fixing parameters. In general, you have some complicated coupling.
Look, I think the answer is what I said, that if you, again, the proof that the Liouville field theory coupled to the fact that you keep the Liouville field theory, you take your CFT and just couple them by terms which are the integration of some operators, if you wish, on the metric, but otherwise you just take the combination of your two Lagrangians, okay? So somehow, but you have to take a certain gamma. I think that's the answer to your question, which we don't have here. So we don't claim to have the gamma here. So to get the gamma in terms of C, you will have to do something else, which we.
No, I'm not interested in that question.
But I think that's the answer to your question. I think you should look at the model of Liouville field theory.
So you say
before.
The point is the Liouville field theory is so simple that it's almost two decoupled things.
Well, it's not so
Therefore,
simple.
you can interpret it as taking.
It's not simple. It's not simple at all. Believe me, look at the way people try to calculate with that.
But somehow, you're telling me that the Liouville field theory has the property that you can generate realization of it by doing two independent things on the different fields And putting them together in a simple nonlinear way.
Good, Alan. Let's put it. Let's discuss upstairs and stop today. Because we don't know how to read a Liouville field theory from the easy model and so on yet. We don't know how to reach. There is still a lot of. What I presented here was that the fact that if you define your random matrix this way, okay, put your fractal, embed your fractal within this random metric, you are going to find KPZ. Okay. Now, if you want to make the complete construction of quantum gravity from the Ising model, your random lattice, go to the continuum, understand what is Liouville field theory, define it properly. Okay. This is what the people are trying to do, but it will take more time.
I see. So you've started from this Liouville field theory.
No. Remember, I just started from no. I just mentioned it because I said we took the ingredients there. But then remember what I did. I defined the quantum area from my GFF, and then we treated the GFF properly.
Right. You took the field theory as the motivation for defining the experiment the way you did.
Exactly. So I gave you first a model on the lattice. People don't know how to derive the Liouville field theory. Once you have the Liouville field theory, if you want to extract KPZ of it, you can start by the way we do it, and understanding the properties of your model. So the key things are the fact that this mean field is a Brown motion, and KPZ then appears as a large deviation principle that people did not know before. Okay. So now you can come and claim, well, you don't answer the question, the big question, so on. But then, I would just tell you start and work because, there are plenty of things to be done.
In a sense, you can stop reading KPZ 88 anymore
Well,
and only use 81 Polyakov.
Exactly. Yeah, exactly. So, huh?
That's a good way of saying it.
KPZ were using Polyakov as well, maybe better.
Well, the original KPZ proof, I frankly don't remember, and it's done with in a kind of gauge called light cone gauge and so on. So it's very hard to follow. Then it was rederived formally by using the Liouville field theory and looking at just the general conformal properties of the Liouville field theory coupled to a CFT. So with standard arguments like power counting and things like that. So it's so this light way of deriving it was done a bit later by Disler, Kawai, and David. And yes, and so what we wanted to do there is which was just to give a different approach by treating the GFF properly. So it's fair. So the point, actually, it would be interesting to see if you do see this KPZ, because as I said, people usually see KPZs with a proper gamma, but when you decouple both of them, you still should have KPZ, and that. So ask people who did simulations. So some people did this kind of simulations by decoupling, and they got kind of so there were two teams in Great Britain, and they usually find contradictory answers. Some people believe that you could still use KPZ like we have. Some people believe you could not. It did not work. So there were some numerical studies done. I don't remember the citations now, but I talked to them but they probably did not have enough statistics.
So
we don't know.
Crazy result for numerics. You're a 91/46.
Well, but but there are many other experiments you can look at. So it's not necessarily percolation. There are other things. People did look at. They call it the wrong kind of gravity. So meaning changing gamma. That's the title you find. And so two teams actually got contradictory results in the 90s. So I don't know more. And I spoke with one of them a few months ago. So
but they were testing.
They said they would try to redo it.
They were testing numerically your theorem.
If you wish.
Which would be unnecessary.
Yeah, but still you want to see if it fits. Otherwise no, people will understand what is going on in the simulations.
I mean, I guess the reason for doing the simulations might be if you have a theorem and the numerics don't fit it, it's suggesting to you that similar numerics in more complicated models are also dangerous.
Yeah.
There may be very strong corrections to scaling or something that make it very difficult to see what you've proven rigorously to be true.
But here it's just hard to do because you are averaging something on a circle, which is not a random random walk, say, because it would have a simple exponent while the exponent is depending with this gamma, but not even something smooth. So it's a fractal with a dimension which depends from gamma. You cannot use a mesh unless it is incredibly fine.
No, but of course, here I took the version which suited us with Scott, which means, you know, taking, being the continuum and doing things nicely on a circle. But you can also imagine to do it on a grid and, you know, take small domains and so on. So that should be equivalent. So somehow part of the proof would be also to show that it is robust to other regularizations. But numerically,
There is something which I really don't understand. There is an asymptotics.
yes, yes.
Where?
The short, when you
Yes, I
shrink.
understand, but I have not seen in the proof where it comes, at what point it comes in.
Because I have,
It is related to what is the origin, because you are neglecting extra.
well,
steps.
but you know, you don't want to be, if you put
No,
yourself,
but that is relevant in numerics.
yeah.
What the problem is what
Yeah,
you
right.
must neglect. At what point have you reached the asymptotic regime? That is
Right,
not
right.
clear.
Well, epsilon must be large with respect to spacing. So in the continuum epsilon is
How large? That-
Epsilon has to be large with respect to the spatial grid and small with respect to the domain.
And well, of course, if you have
As
this
usual.
every time, even in intercollection, if you want to understand this arm exponent with the two radia, the ratio of the two radia must be large, and the small radius must be large with respect to the spacing. That's just the definition. And if you want to do numerics for these really huge rationals, you should have a huge lattice. The proof is simpler than the numerics, even the stupid one.
That is the problem.
well, I think I re-exhausted the, thank you for your attention.